Hello everyone and welcome to ST300, and now we are in week 4. And today's topic is diagnostics, which is a continuation from last week's lecture. So the story so far is we've derived the sampling distribution of the OLS estimator under the standard assumptions. And we derived the general test for the general linear restrictions, which encompasses F-test for overall restriction, F-test for overall significance, T-test for individual significance. And then we finished off by looking at confidence intervals for the parameters and the mean of the predicted value and prediction intervals. So today we're going to be revisiting the assumptions, the standard assumptions, and to see what the consequences are to the OLS estimator when each assumption fails, how we can detect violations of assumptions, and how to deal with the violations. So the diagnostic, these are what are called the diagnostic checking for checking the assumptions. And there are kind of two approaches. There are test-based approaches and plot-based approaches. In this course, we adopt the plot-based approaches. Test-based, hypothesis-based approaches, that's usually covered in a course in econometrics. I want to emphasize at this point, guys, there is no unique model that meets all the assumptions. And so that means there has to be some kind of subjective choice here, that you have to pick among competing models which one is the best one. To show you where this diagnostic checking fits into your workflow in building a model, here I have flowchart. And what you can see is that model building is an iterative procedure. So it starts off by proposing a model and estimating it. Now then, here with the next step, you do your checks, model assumptions. And then if you have violations of the model assumptions, you kind of deal with it somehow, and then propose or adjust the model and repeat. When you get to the stage where all the diagnostic checks are met, then you are ready to interpret the model. Now, it's important at this stage is to say that, okay, so you come up with some statistical model, or maybe models, because you may have several models that pass your diagnostic checking. Then if you are trying to build a model to explain phenomena, the relationships between the covariates and the y variable, what you should be thinking about is compare it to what you observe in the real life. Do these kind of models make sense? For example, if you expected a positive sign on a coefficient and it's negative, well, can you explain that? Does it make sense? Now, this workflow I've shown, what you see in front of you, I just say is not like the workflow. So it depends on your purpose of why you're building a model. So a person who is like building a model for prediction, typically like with traditional machine learning methods, they will have a different workflow. So the workflow here is really one just to show you that we can, what you should do if you want to test the assumptions of a model. And maybe this one's better if you want to explain phenomena. But even then, as I said, you have to be careful because this such a model that comes out of this process does not mean it explains cause and effect relationship, as we'll see in a moment on the next slides. And maybe I want to link this to real life data analysis. So if you're in a company and you have to create some kind of a model, regression model, say, there's a question mark over how much diagnostic checks people actually do in workplaces. Maybe some of these assumptions are more important than others, such as you've heard of outliers, what we call influential points, actually. Some people in some workplaces, that is more important than doing all the other checks. Okay, but for purposes of our course, this is kind of the workflow that you'll follow. But just bear in mind that in reality, this is probably not what you actually do. You'll do some modification of this. All right, so let's look at an example now of trying to explain phenomena and what we should be wary of when we're kind of coming up with a model. So one of my favorite examples is like headlines. Health headlines, okay, are designed to grab your attention. So beware of them when you see them often in these newspapers. So do you have 2 or more children? If you do, you're at risk of heart disease. So this was reported in several newspapers, but it's from some clinical data. So let's say we've got some data for this and we fit some model. So we have the probability of a cardiovascular disease. Okay, a simple linear regression model is some function of a number of kids parents have. And so the question is this a cause and effect kind of interpretation? In other words, do we have a direct link between the number of kids here to the chance of a heart attack? So the question really is, when you have fit a model, is we're interested in the mechanism that underlies the observed relationship between the X variables and the Y variable. So is it as simple, this model here would be interpreted like this. The question is it so simple? So say you have a model and you have come up with this guy here, this equation, this model, and it meets all your assumptions. Well, is it as simple as that, or is it as more complicated like this? So in this case, you see that the path from the number of offspring to the CVD is more complicated. So it may not be a direct causal link there. For example, you have this variable here, C, social economic status, that is a confounding variable because it is associated both, or it causes both the Y variable and is associated with that X variable. And you have these other possible paths as well also. So instead of having number of offspring directly related to CVD, it acts through these some other variables, which in turn act on your Y variable. And such variables are called mediators. So if you come up with a model, you have to think like, I'm trying to explain this real world phenomena. Is my model, does my model capture the mechanism? So you might think of some kind of a graph here. We call these DAGs, directed acrylic graphs. So these guys are called nodes, and they're joined by arrows, and the arrows here show you the direction of relationship. Okay, so coming up with such a graphs here can help you understand, is your relationship like this, or is it just like this? I'm not saying it can't be as simple as this for some mechanisms, but you should always think about that when you fit a regression model. Now, the thing is, like, if you have fit a regression model and you don't have these variables, then at least that is something to discuss. You see, this is where domain knowledge or expert knowledge in the field comes handy. So when people fit these molds and they're thinking about the mechanism and not sure, they can sometimes contact people, domain experts, and like in this case, like maybe health clinicians, and ask them what do they think are the actual causal links here. So at the end of the day, if you want to explain phenomena, remember the regression picks up associations, but not necessarily causal and effect relationships, not unless you take account of all like confounders and, for instance. Now, in this slide, we're going to motivate why we have to, some issues that arise when we fit a regression, and that's why we need some of these diagnostic checks. So here's simulated data. 4 simulated data. It's from a famous data set called Anscombe quartet data, after this guy called Anscombe. So simulated data set, in each case, when you regress the y on the x variable, you get the same regression line, i.e. the same intercept and the same slope. So look at each of these guys here and think to yourself, which one seems most reasonable as a regression line? So A, I hope you think that A is reasonable. The others, there's some issues. So with B, you can see here, the straight line does not capture the functional form here, which is curvy. In C here, you see there is one point out here, and that is kind of distorting this line. In the final case here, you see this actually the slope of this line is determined entirely by a single point. So that is very worrying, right? So the point is like down here, it will be exactly very, very different. So without that point, there's nothing, no apparent relationship. So this part D is more extreme case of C. And we'll be talking about these later today. Incidentally, on the side here, I've shown you the code on how to generate these plots. Now, just to say, point your attention to the fact now, I'm not using ggplot, I'm using this plot function, which is inbuilt in R, core R, so there's no packages here. And you can see that the plots are still very visually appealing, although less flexible than if you use ggplot. Now, on this slide here, I've summarized basically an entire lecture's worth of what happens when you have the assumptions which are violated, what is the consequence to properties, statistical properties of your OLS estimator, how you can detect the violation, and what you can do about it. Right, well, this is one of those slides that I just say read really. But let's kind of point out the main things. For the assumptions A4, A5, if either of those are violated, it's the same kind of leads to the same consequence for OLS, namely OLS is still unbiased, but it's no longer efficient, no longer the best. So you can find a smaller standard error. Indeed, the standard errors are wrong estimated in this case, if you don't take account of the fact that the violations, these violations, and so tests are not valid. How do you detect it? Well, we can look at that. We can kind of visually detect it by looking at residual plots. How can we deal with it? Well, we can use some kind of a variation on these squares, the OLS estimator, called the weighted least squares, which we'll look at shortly. And we can, not covered in this course, we can use what we call robust standard errors. That just means that it's just adjusted standard error formula. The normality assumption, if that is violated, OLS is still best in the class of linear unbiased estimators. It does, however, affect the inference in that the OLS, the sampling distribution we derived in previous lectures, no longer exactly normal. But people kind of place too much emphasis on this assumption here. If your assumption does not deviate from normality too much, it shouldn't matter too much, because by CLT, and you have a massive sample size, then your usual test will hold asymptotically. Now, of these remaining ones, this influential point we're covering today, and this multicollinearity one we're covering next week. Okay, yeah, and this one we're covering today. All right, so this is a slide that you might wish to come back to. Right, so the residual plot, what is the residual plot? It is a scatter plot where your vertical axis, the residuals, and the x-axis, the horizontal axis, is either the index of the data, the covariates, individual covariates, or the fitted values. Well, for multiple linear regression model, we would usually have on the horizontal axis the fitted values. And for simple linear regression model, it doesn't matter if you have the fitted values or the xi or the x variable. The plotting against the index of the data, that is like for time series. So then the index is time. Now, what we're looking for, well, we're looking for that the residuals fall in some kind of a narrow range, because that will imply that we have a constant variance assumption satisfied. We look for regression outliers. And if there are any apparent outliers, we'll follow up to see if they're influential, to be explained in today. Now, it turns out that the residuals are better to determine if they're regression outliers. It's better if we plot the standardized residuals. In other words, we kind of, as you understand by standardizing, so we'll make them to have about a set unit variance, so that they're comparable. Because it turns out that residuals, even if the model assumptions are satisfied, that residuals are satisfied, that they don't have constant variance. Okay, now final one about this independence assumption that we said, maybe we said it was that the covariance between the error terms is 0, but coupled with the normality assumption means that the error terms are independent. Well, for cross-sectional data, this assumption is met if we have a proper random sample, so we'll assume that we have that. But presence of missing values can make this assumption fail. Now, if you're doing time series, then you can test this assumption, and you might see that in ST300, but that's not something we do on this course. Hence, that's why I said in the project, do not pick time series data. All right, to show those features that I've just looked at, so let's look at this. This is, I'm going to simulate some data. So the first plot here is y versus x, where I've simulated all this data. And then I fit a simple linear regression. And then I output the residuals. And so ideally, this is what you should see. So I have residuals here, and I'm plotting against x-axis. Now, if we look at the scale here, it looks like it's going from 6 to -6. Now, to better spot outliers, we standardize instead. Instead of looking at the residuals, we plot the standardized residuals, which is in this third plot here. Now, it's more narrow, and I've drawn here the bands plus or -3. So anything falling outside that, we'll kind of consider as a regression outlier. Now, so let's look at the code, how I've simulated this data. I've done this in 3 steps. So simulate the data, I fit the model, and then I output the residual plots. Okay. So first of all, I need X's and I need the Y's. Okay, so simulated data just means I make up this model from some model that I create. So instead of finding the model, you pretend you're God and you make the model, and then you generate the data from that model. Okay, so I go X is equal, and then R norms generates values from the standard from the normal distribution, 100 observations, with a mean of 40 and a standard deviation of 1. And then I'm going to generate Y as saying that the intercept I'm going to have as 1 plus, and then I'm going to set the slope parameter to be 2 times X here, which I've generated up here, and then I'm going to plus the error term. So it's going to have a mean of 0 and a standard deviation of 2. Now, there's no reason why I have to set intercept to 1 and the slope to 2, and you can change that. All right, it's just simulated. I'm just pretending that this is the model. The main thing is that I'm going to actually fit a simple linear regression. So I'm going to suppose I've got the right functional form. Now, this set.seed here, this is optional, but it's placed here so that if you want people to be able to reproduce the exact results like you do, see what we have in the line 4 and 5 is I'm doing random sampling. And when you're doing random sampling, actually the random numbers are generated from some deterministic function. Okay, so it generates a sequence of numbers, but the sequence of numbers needs an initial value. So you can think of it like initial value. So the initial, so it's like thinking, what is the initial sequence begin with or something then. And so what we do is we do set.seed, and then we put in the parentheses here any old number. But so long as we have the same number here, I put 124, but it doesn't mean anything here. I could have put 1, I could have put minus 1.236, not anything I like. But so long as we all use this number in the set.seed before we generate the random numbers, we'll get the same random numbers. So you might want to try this with my random seed and without. Okay, so that's step 1. Step 2, now I'm going to fit the model. So LM, okay, I'm supposing I've got the correct functional form here. Now notice I don't have to do comma data equals. Why? Because I did not save X and Y into a data frame. So X and Y would be saved in my global environments as individual variables. So when I write this, I'll look for these variables directly there, and of course they're there. All right. Okay, I'm going to call this regression object this guy here, but maybe better word for it would not be to use a dot. Maybe m_sim would be better. Okay, now I'm going to plot this. I'm going to plot the scatter plot of the data here. And I'm going to use it using the built-in graphics capabilities in R. Because I'm going to draw 3 plots on the same graphics window, I'm going to set my graphics window first. So I'm going to set it to be a grid of 1 row, 3 columns. And what I do is par stands for parameter, and then mf row stands for multiple figures arranged by row. Okay. An alternative one is mf col, multiple figures arranged by column. So you can try that. Equals, and then this is like a vector matrix notation. So I got to 1 row, 3 columns. And then I plot my first scatter plot. Okay, so this will be in first position right here, leaving a space 2 and 3 for the next 2, which are going to come along. Okay, so the next plot I do then is this one here, with residuals against the X variables, and you can see exactly what's going on here. I've got X. So what comes first is always the thing on the horizontal in this plot function, comma, and then the thing which coming up on the vertical. Now the model regression object has an attribute called residual, which if you remember last week's lecture, I also used. So you can access that by doing the $sign and then res or residual. So last week I used res in the lecture shorthand because it understands. And then these other things are just labeling and setting up the axes. They're optional. So y lim, so it's the limit of the y-axis values. I'm setting it going from -7 to +7, but it doesn't even have to go there that far. The y labels, okay, so I'll label the y-axis, and the x-axis I've labeled that as well. And then finally, to do the red lines here, the red lines are just to help to pick up any abnormal values, i.e. outliers. I'm going to use AB line. So AB line, A stands for intercept, B stands for slope. AB line, where the A is 6, so and B is 0. So I've got one of the lines there. All right, L, this is not 1, this is LTY, stands for line type, equals, and then some number. You can try what you can put different numbers here to see what the options are. Just look up the argument online. And the color, well, instead of saying color is red or anything like that, it does it by number coding. So again, you just have to look up online just to see what color options are available and what the associated numbers are. All right, and then line 13 obviously does the same thing, but gives me the lower line. It doesn't matter like why if I pick 6 and -6, I've just picked some number so that I think that if it lies outside, it is something which is extreme. But remember, the second one is not that useful for outliers because these residuals have different variances, even if the model assumptions are met. So what we do is we standardize them or look at some standard version. And that's what I'm doing in the third plot. So everything's the same, guys. All I'm going to do this time is I'm going to look at the standardized version. And the function to do that is R standard. Just to say there's actually different versions of standardized residuals. So you hear of these things called internalized and externalized standardized residuals. Not really, to be honest, that's just minute, a very subtle difference, not practical, not important practically. So I'm just using standard here. So just know that the idea is to have the variance. This is about 1 for the residuals so that they're comparable. And now the assumption, if the assumption of normality is satisfied, you guys know like about approximately 95% of the residuals should fall between plus and minus 1.96. In practice, people can set then the boundary to be plus or minus 2 or more extreme plus or minus 3. I've just done plus or minus 3 here. Okay, now because I have simulated the data, so I know the true data generating process and I fitted a line here. So I've got the correct functional type. I don't expect to see any outliers and I haven't. Okay, maybe a point here before I go on though. I'm going to slow down here because although there's no theory here, so it's very easy just to whiz by this very quickly, should still have to do some thinking here. Look, suppose the distribution of these error term and hence residuals is normally distributed. Does that mean you don't get any residuals falling outside plus or minus 1.96 or plus or minus 2? Well, the answer is that you can expect a few values to fall outside, right? So that why? Because, well, because of the shape of normal distribution, it allows for observations falling beyond plus or minus 2, but proportionally wise, very, very small, very, very small. So if you have a massive data set, don't be too bothered if you do have some falling outside. Okay, there could be outliers, but anyway, does it even matter in that case? All right, so here's another plot here, but just shows you the same kind of thing here. Now, what we can spot is, so the first plot here is again residuals versus fitted. Just imagine it says standardized residuals. So the first one suggests no change to the current model. So this one shows like it's like no problem. So maybe it's like there's no outliers here, and that's fine. It's centered around 0. Okay. So just imagine drawing, if this is an exercise for you, draw y, this is for a simple integration model. So above this graph here, think about how you come up with this plot. So you're going to have y, x, you have some dots all over the place. So you put a straight line, and then you can create such a residual plot. Now, for this second one, you can see that it's centered around 0, symmetrical around 0, mean of 0. But you can see the variance as we're going scanning along is increasing across the fitted values. So the variance is not constant, it's growing, it's increasing. Okay, this is a case of what we call heteroscedasticity, as opposed to homoscedasticity, i.e. you have non-constant variance of the error term of observations. And recall what that means. It means that the OLS estimator remains unbiased out of but no longer best out of class of linear unbiased estimators. More of the standard errors are incorrect. So you've got problem with conducting tests and confidence intervals. This final one shows you've got this curvy relationship here. And then that is basically you have not captured the functional form correctly. So this guy here, if you get such a residual plot, points to, if we go back to the second slide, such a situation of y against x will create. You can see this curve already. That curve will become apparent when you sketch the residual plot. Basically, this line here would, in your residual plot, would be your kind of horizontal axis. Then put your vertical axis this way. This would be your residuals. Then you can see that you've got a curve. Right, so the residual plots is like the most basic of all of the plots, and there are tons of plots, and we're not going to see all. We're only going to see a few plots. I did say earlier that even under the model assumptions that the variance of your residuals will not be constant. Now here is the reason why. So under the model assumptions, the expectation of the residuals is 0, but the variance, okay, is not sigma square I. Okay, so the variance of the variance covariance matrix of your error term under model assumptions, remember, was sigma square times the identity. This one is this, all right, which can be proved using that. So I'm tempted to show you that, but I shouldn't, because you should do this, right? So just do this as a small exercise. Take the variance of this guy, it's equal to this guy. So element wise, if we look at this, what does the diagonal elements of this guy looks like? It looks like this. And now you can see that the variance of the error residual, sorry, is not constant because it depends on the diagonal matrix of your hat. Depends on the diagonal element of your hat matrix, which is obviously different as you go down diagonal, and so it's varying. The covariance also is not 0. So remember the assumptions, we assume that under the model assumptions, one of the assumptions was that the covariance or correlation between two error terms, distinct error terms, they are 0. But here, I mean, for the residuals, they're not going to be 0, not unless your element of the ith jth element of the hat matrix is 0. So up to on this slide, you can see from the present discussion that the hat matrix has an important role here about the properties of your residuals. So that goes back to say why I've just emphasized when I first introduced the hat matrix, why it was important, that it is very important in regression theory. Okay, so based on the arguments, as I said earlier, for fairer comparison to see if we have any outliers and such, we can standardize. Okay, so we standardize. Now we replace the sigma square by s squared, which remember is the estimator for the variance of the error term. So that is RSS divided by n minus p. So that deals with the residual plot. That's one of the basic plots. Another of the plots that we should look at is to check for normality. And okay, people kind of are more comfortable with when you first learn statistics with histogram, because you see that at school, but a better one is to look at the normal QQ plot. So here I'm just going to show you side by side histogram and the associated pattern of the normal QQ plot. Right, so this top one, this top row here, we've got some normal distribution. Okay, that's the histogram. And beside it, we have the associated normal QQ plot. Now, normal QQ plot plots the theoretical quantiles versus the sample quantiles. You don't have to understand exactly how you're going to construct the sample quantiles from this. But just note that underneath here, these circles here, these are the data points, is a line, and that line is a 45-degree line, so it's mapping y equals x kind of thing. So -2 here to -2. So basically it's saying that if your sample quantiles agree with the theoretical quantiles that lie on this line here, that you have your data follows a normal normal distribution. So you see here it's very tight on the line, which is to be expected because I'll actually simulate the data from the normal distribution. The second one here shows what happens when you have something which is positively skewed, and then you can see your normal QQ plot. You're looking for the shape. It's bending upwards in the right tail. Okay, so this is the right tail. This will be your left tail. This will be like around the center of your distribution. You can see if it's a normal distribution centered about 0, that is like the peak of your histogram here. And then just swap the argument around. If you have a negative skew, then now you have the tail bending downwards in the left tail. One thing to add more, if I had another example to give you, is that you can combine the second one and third one to get to see what you have when you have a distribution which has called long tails, right? So I say that because maybe in some applications like in finance, you have long tails or insurance. So you can combine that, a long right tail, a long left tail. So you would have, what would you see? You would see it sloping to the upwards on the right, and you would see it sloping downwards to the left. In that case, your distribution has long tails on both ends. How did I generate this data and the plots? Okay, well, I set the sample size first. Okay, so for the first plot, I'm going to create samples from the standard normal distribution. And then for this plot here, I'm going to set the graphics window first to have 3 rows and 2 columns. First plot is the density of Z, which is the standard normal. And then I want the QQ normal plot. Now, function to do that is, and again, this is the inbuilt R graphics now, not ggplot. We call QQ norm Z. And I superimpose that QQ line. So that gives me the line. This semicolon here is just another way of saying next line. So instead, just save me space. Instead of putting this guy on line 31, I can just do this guy, and then it understands this guy is another separate function. Okay, but probably you shouldn't do this because it's easier to read if you just put it one under the other. All right, and then similar story going from the second plot that I'm going to generate using a gamma distribution. Gamma has 2 parameters here, so I've created such that we'll have a long right tail. And the third one I've, to get this left skew, generated using a beta with the parameters 11 and 2. Now, caution has, wherever looking at interpreting plots, we always have to be very cautious when we have small samples. I'm going to show you in the next plot. When we have small samples, do not interpret every single wiggle as if it's actually meaningful. So again, I've actually simulated data just like before, but now I've changed the sample size, I've lowered it. And in the first case, it's still, the data is still from a normal. You can see the histogram is a bit bendy here now, not very normal-like. And you can see there's some deviations to the ends. But notice also the density of the points is less now because you have fewer data points, and each circle represents a data point. So around the ends here, so if you have a few data points away from your line here and sample size is small, you shouldn't kind of pay too much attention. You'd expect some anyway, even if you had a massive, large sample. Positive skew, okay. Negative, okay, so all this is just giving you an idea of how not to interpret the plots. So when we have violations of these assumptions, now we're turning to the remedy, so you can refer back to the table. So when we have violations of some of these assumptions, we can think about the strategy of applying some transformation on the data before applying OLS. And that is the idea of weighting these squares, and down here as well, for linearity, for violation of linearity. Okay, so why do we apply transformations again then? To straighten out the relationship when the relationship between the predictors and the y is nonlinear. That would be this case. Instead of regressing y on x, hopefully you can imagine that you're regressing more like y on x squared. It's more like a quadratic thing. We can apply transformations to make the residuals more normally distributed, more symmetrical. Now, but which one do you transform? Because we can transform y's and we can transform continuous x variables. Do we transform one or the other or both? Well, here is some kind of things that you can try. We consider transforming y variables only when we're faced with non-normality, and or if we have heteroscedasticity. We can think about transforming our covariates when we see a nonlinear pattern, and that is the only issue. Some examples of what we might use as transformations then. If we have like a y versus x, say, and we see this kind of curve, well, obviously it's not a straight line relationship then. You could try this transformation, square root transformation. And if you have a curve bending up this way, you can try, I'll start again. If you have a curve going this way, it's more like a relationship of y equals not a function of x, it's as in a straight line, it's like a y equals logarithm of x. So then your transformation would be regress y on log x. This one here, it's bending upwards. You might try, therefore, having a regressing y not on x, but on like x squared, or since it could be even an exponential of x. Right, and this guy here, you could do 1 over x, either reciprocal or exponential of minus x. Okay, now, if we're in a classroom setting, I will set you this question and ask you, but you can still think about it. I'm going to simulate 100 observations from this model. Again, I'm God. I've created this model. I'm just generating data, the x and y's, and I'm going to give x and y's to you and ask you fit the model to this x and y. Can you come back up with my model, the data generating process, DGP? And I'm supposing that x is normal. Now, there's no reason why I have to suppose x is normal, but I am. I do need to suppose that the error term is normal, though, because that's the assumption. And has constant variance. So regress y on x. If you regress y on x and we look at the residual plot, it looks like this curve, right? So I've got the y on x. I've generated 100 observations. It looks like that. You fit a straight line, and the associated residuals look like that. Well, based on this, what is the relevant transformation for x for the simple linear regression model? Would you think it's A, B, or C? Now, just in previous years, right, you could pause the video and have a think. Now, previous years, I remember asking students in the class setting, lecture setting once on this question, and the majority vote went for B. Now, it isn't B. It's, you could either go, if you only see the y and x data, or you only see this plot here, would be acceptable if you went for A or C. But actually, the answer, of course, is C, because you can see right here, e to the x. In practical work, in terms of transformations, actually the log transformation tends to be most common that you see. So why log? Well, just look at what a log transformation does to the data. So it preserves the order of the data. So here, just think about the shape of the log function. So it preserves the order of the original data, i.e. if A is bigger than B, then after transformation, your new A is still bigger than the new B. And it makes a positive skew distribution more symmetrical. So you can see here that if your error term is kind of positively skewed, then this transformation could help make them more, on the y variable, make the residuals more symmetrical. And it can help with linearity as well, and heteroscedasticity. Now, if you apply the log transformation on the y, x, or both, it changes the interpretation of the slope coefficient. So let's look at that now. In the following interpretations, we'll have x as continuous. Okay, case one, you take the log of y, but you don't you do not transform this x here with that. So this is what we call the log level model, or log-lin model, some people call it. And interpretation here is of the slope coefficient is you have a percentage, it has a percentage interpretation when multiplied by 100. And you can just read here what it says. If you have transform both sides, log-log, this tends to be quite popular in economics, economic models. What you get is beta, the interpretation now is what they call elasticity of x with respect to x. That's kind of economic speak. So this tells you what it means. So it's like percentage, it tells you percentage change. Percentage change in your input, 1% change in input leads to an average to a change in y by beta 1%. Now, can I just say on this slide, as opposed to the next slide, I just want to go back to the first lecture about interpreting the coefficients, is that when we make the interpretations this way, it's like the interpretation is from a causal kind of interpretation, cause and effect type relationship, because you're saying a change in the input leads to some kind of a change in the output. That is a causal interpretation, but you have to be very cautious because it's likely that that is not the proper real interpretation, i.e. if you actually physically go out and what they call do an intervention, you change x by something, that it actually leads to change in y by that something. For example, the example we've just seen today about kids and the probability of or risk of CVD. So probably, I mean, the interpretation is easy to say this way, but it's also misleading. It's what we want to say, but we just got to be careful that we have the right mechanisms before we can actually say it this way. So in terms of this interpretation as an association, we should maybe less misleadingly say that if X, the interpretation of beta 1 is if X takes like a particular value, and then we compare it to an X which has 1 unit greater than the X that we had, then the differences changes such and such. To make it clear that we're not actually performing kind of any intervention here, okay? That's if you want to interpret it as an association. Okay, and then there's nothing more for me to add about this interpretation. So finally, we have do not transform Y, but do apply a log on X. Now, the three interpretations here is just like in the simple linear regression setting, but it applies to multiple linear regression settings too. And you can have a mix of, like in this case, X variables here. This X is not, say, X1 here is not transformed. And then you have beta 2 times log of X2, okay, plus the error term. And that's multiple linear regression setting. In that case, the interpretations of the slopes are still kind of as you see on the slide, except for you have to say ceteris paribus, i.e. controlling for everything else, if that is possible. But we say that. All right, so more technically now, another transformation is where we apply transformations to the original regression. In the regression setting, this would be in the matrix form setting, guys, of the regression. This would be like pre-multiplying your left and right hand side of the regression model by some constant, by some transformation matrix. But let's do it without matrices to show you the idea. So consider that we have this regression model. Note that in this case that the variance of the error term is not constant. That's why it's got a subscript I here. It may vary. How does it vary? Well, let's suppose it varies like this. So it's constant for I less than some value of B of these observations, where of course B is less than, let's say, less than N. And when it's bigger than B, it becomes this, where A is some constant, which we know. So how do we kind of, so problem here is got heteroscedasticity, and so that invalidates our hypothesis testing. So how can we deal with that? Well, we can think about this by applying some transformation, and for I less than equal to B, that's variance is sigma square. Now, if for all other observations bigger than I bigger than B, if we pre-multiply left and right hand side by 1 over A, so now our new error term here is like this. Now, what's the variance of the new error term? Well, variance of the new error term will be sigma square. I'll leave that to you to calculate. It's just no matrices there. You should be able to show variance of this guy is sigma square. So by pre-multiplying the second part of the data, for observations bigger than B, by 1 over A, the variances now match. So now we have constant variance. And now that means we can apply the usual least squares, the ordinary least squares. Okay, so now you see why we put O in front of least squares. So the weighted, and this is what we call weighted least square. So we kind of apply some transformation to the data, to the model, sorry, and then apply these squares. All right, so here is a matrix form, as I said now. So we find some kind of a matrix. W, square root of W here, let's call it a matrix, let's call it square root of W. Apply it to left and right hand side of your Y equals beta, X beta plus error term. So you imagine removing this first, that is your usual regression there, y equals x beta plus error term. Then I'm just pre-multiplying left and right hand side of the equation by this matrix. And in our case, then this matrix, transformation matrix, is a diagonal matrix. And then our error term here will be multivariate normal and satisfy usual conditions. And if we apply the solve this now by least squares, OLS, this is the estimator. And this is what we call the weighted least squares estimator. So W here, consider as the weights. Okay, now, so here is an example, and I'd like you to attempt this before you actually watch me solve it. So for that, I'm going to just have a pause here. Write down the covariance matrix of the error term. So the variance of the individual error terms, is not constant. So we have a problem of heteroscedasticity. Variance of the error term. This is n by 1, and the whole thing, variance covariance matrix, is n by n. Because we have n observations. Now we're told that the error terms are independent, so that means the covariance matrix between the error terms, distinct error terms, that are 0. And so that basically means that this variance covariance matrix only has the variances, and everything off the diagonals is 0. That is what we call a diagonal matrix. And a shorthand way to write that is we just write diagonal. And so the first element on the diagonal, the top left, is this guy. And yeah, and so that's what it means. Okay, so this is shorthand for that. All right, so we have answered this, and what assumption has been violated? Assumption of constant variance. Assumption of constant variance of the error terms over observations has been violated. Assuming the xi's are non-zero, then what is the covariance matrix, okay, of this error term? So it's based on the transform ones where you divided each one by the observation, by the predictor value. Hence suggest a transformation of the model assumptions. Okay, read it through, guys. Okay. So the covariance matrix of this guy, let's do that first. Well, the variance of an individual, a scalar value here, so epsilon I. And since xi is a constant known, so the variance of the epsilon I is known, and it's sigma square times xi squared. As for the covariances, they are 0 for distinct error terms, because we're told that the error terms, the original error terms, are independent. Okay, so taking those two together, the variance covariance matrix of this transformed error term all right, which satisfies the usual assumptions that we need. So what does that suggest? Hence suggest a transformation. Well, the suggestion is basically looking at as he's done it. So it's multiplying your regression model by 1 over xi. So the transformation that's what I'm looking for. So I was just looking for something. There, that's it. It's worked. That's good. Right, so transformation. Yeah. Right, now what is my intercept, guys? Is it beta 0? It's beta 1. What is the slope this time? It's beta 0. Right, now we have constant variance, you see. Right, yeah. So the standard linear regression, the assumptions now are satisfied. Okay, and then finally write the transformed model in matrix form. That's n by 3 matrix. Now the beta here, notice then starts with beta 1, beta 0, and then beta 2. Transpose the, okay. Before leaving the weighted least squares, just to say that we will be looking at weighted least squares again in the second half of this course. That's why it's important that I've introduced it here. All right, so we've earned a break. So I'll see you after that. Welcome back. We have now covered the cases constant variance and independence, normality, and that leaves for today the linearity, where we want to detect for nonlinearity, and we're looking at influential points. Okay, so to discuss the influential points, we need to know what we mean by a regression outlier. So a regression outlier is a large residual. Notice the word here, I put regression outlier, where it's clear that what we're dealing with is outliers in the regression model. We can just use the word outlier. But otherwise, you shouldn't kind of make it clear by saying regression outlier. Because if you think about first year stats, ST102, when you looked at outliers, maybe in the context of like a box plot or something, an outlier, that would be a univariate outlier. If you find an outlier in a box plot, univariate because you're only looking at a single variable. So it turns out a univariate outlier need not be a regression outlier. And then we have to, we'll kind of define what we mean by a leverage point, a high leverage point here. And that is like an extreme predictor value or values. An influential point is a point that kind of has considerable effects, maybe more than it should compared to the other observations. And when people talk about outliers outside of regression, they usually mean that the point is influential. But we'll make a distinction here, because it turns out that a regression outlier need not be an influential point. But now let's look at how industry considers these influential points. Going back to the interview in the Harvard Business Review. So the decisions you make as a result don't have a big impact on your business decisions, then it's kind of okay if your data is kind of leaky, i.e. maybe with some issues there, such as with regression outliers, influential points. It does matter more though if you're going to build this model to make some decision which is going to end up costing, which is costs quite a lot of money. Right, so the case here is that a regression outlier or a leverage point alone is not so critical in terms of affecting your output. So what we're interested at the end of the day is, are the points influential? Right, here are a couple of cases, A and C. So in the case A here, I show you in this simple linear regression that we have one point over here. Now, suppose we don't have this point here and we fitted a regression line, it would be, okay, this is what it would look like. Now, suppose we fit the regression line with this point included. Then what you can see is the line now has moved to the dotted line. So it's adjusted slightly. In this case, this is still a large residual. And so this point in yellow here is a regression outlier. But is it influential? Well, it's not really distorted my fit too much. It's changed the slope parameter slightly, but hardly anything. So therefore, it is not influential. So we would not worry about such a point. We do not need to do anything here with that, I mean, in terms of adjusting for that point. All right, so that's a case where we have a large regression outlier, but it is not influential. Plots B and D. This is a case where we have now consider a point of high leverage. So point of high leverage is like a point of points which are far from the other points in the X direction. So here, the main mass of X's are in this interval. I'm going to highlight over here in blue, right? They fall onto this interval, and we've got one way out here and another way out here. So these 2 points I would call points of high leverage. We will be making a more mathematical definition in the next slide, but for now, just imagine it is this. That's kind of what it is, just far away from like the centroid of in the X direction. So it does not depend on Y values. Again, fit the regression line. Supposing we do not have either of these points of high leverage. Okay, it looks like this. Now, suppose we fit the regression, supposing we have these 2 points of high leverage. Notice now the line has moved drastically, right? So the slope coefficient has changed drastically, and so has the intercept. Now, why is that? Well, it's because of this point right here. So it's kind of dragged it down, okay? This kind of point, why it's called high leverage. It's got, it pulls like your regression line, so to speak, towards it. So it has a big influence here. And so that this point here is what we call an influential point. In this case, not only is it a high leverage point, it is also like a regression outlier. But a small outlier. But it's yeah, it's still influential. So mathematically, no surprise, we're coming back to this hat matrix here. The ith diagonal element of the hat matrix is called the leverage of the ith data point. Okay, so this x here, it is a vector. The end one is a vector. Let me write something here. So the HII is the ith row and the ith column of your hat matrix H. Now, in general, guys, if you wanted the ith row and the jth column of a matrix, what do? You multiply you multiply and pre-multiply by some special vectors here. So this vector here will be the vector, in this case, it's a row vector where you have 1 in the ith position and 0 everywhere else. This guy here is a vector where you have 1 in the jth position, 0 everywhere else. And such a thing will pick out the ith jth element of this matrix. So the hat matrix here is the ith. So I'm going to have I there and ith there. And when you apply it onto your hat matrix, that's how you get out this guy and that guy. Is one way to see it. Okay, so as a guide, as I do say as a guide, because this is not like, it's very kind of subjective now, what we're talking about. As a guide, we say ith point is a point of high leverage if it's very big, right? What do we mean by big? Well, if it exceeds some value, threshold. Well, what is that threshold? Well, we'll say if it's a threshold, if it is this on the right-hand side, where P is the number parameter, N is the number of observations, K here is up to the modular, typically set to 2 or 3. Now, to understand what this right-hand side, why we have this, we need to know some properties about the leverage points. So if we sum up all your leverage points, it comes to P. And leverage points is between 0 to 1. So what this P over N is saying is the size, the magnitude of the average leverage point, yeah? The average point. I mean, average leverage value of a point. And so if it's bigger than the average, some kind of multiple of the average size you can expect, then we'll call it a point of high leverage. Again, subjective. There's no reason whether you're picking 2 or 3. If you're more conservative, you might want to pick a lower value. But at the end of the day, remember, it doesn't matter whether a point is like a regression outlier or a leverage point. It matters like if they're influential. And whether they're influential turns out to depend on the size of the leverage and how big is this regression outlier. So we need to determine whether a point is influential. We need to take account of both those things. And you'll see shortly, we're going to combine both leverage and outlier value into a single measure to measure how influential a point is. Okay, yeah, so this is a slide I already talked about. So I've just emphasized one more time. So a leverage point, if the leverage point is high here, HII, remember it's between 0 to 1. So if its higher is close to 1, this variance of the residual will be small around that at that point. Why? Because intuitively you can see what's happening with this guy here. It's pulling the line towards it. You have a smaller variability around the line, around the point. So whether a point is influential, then, yeah, I'll repeat one more time, depends on the degree of how large is the outlier and the size of the leverage. Now, two popular plots for finding candidate influential points is a Cook's distance and the added variable plot. Now, both these are plots, but they're used in interpreted in slightly different ways. Because of how they're constructed. So the Cook's distance asks the question, how much do fitted values, the y-hats, change when individual points are removed in turn, like individual data points? So it's going to go through I equal 1 to n. Each time it's going to pluck out one observation. So the first step, it will take out the first observation, fit your regression model, and then evaluate. Then next step is going to take out the second observation and fit the same regression model, and then see how much the parameter estimates have changed, and so on. I mean, change compared to like if you didn't take out any points. Yeah. So we put them into a single measure called the Cook's distance, and the Cook's distance for the ith data point is given by this expression. Now, the only thing to see about this expression, it is a non-negative, takes non-negative values. I'm going to highlight the thing on the right-hand side here, which shows you that this guy is a quadratic form. Okay, and it's positive definite, because Gram matrix is. And this beta here, let me highlight it. This one with the subscript I in the parentheses, this denotes the vector of the fitted estimates when you remove the ith point. Okay, so then what we have here, like these differences, is looking at the difference between your vector of parameter estimates without the ith data point compared to with all the data points. So the idea is like if a point is influential, if you remove it, then this difference is going to be large. Now, if your ith data point actually removing the ith data point makes no difference, then the difference is obviously 0. Then Cook's distance would be 0. Hence, Cook's distance, large Cook's distance, will flag up the possibility that what you have is an influential point, the ith data point. Alternatively, instead of writing like this, you can see that, make the substitution, you can write it in terms of comparing predicted values instead of comparing changes in the parameter estimates. So how big is big to be worried about? Well, this Cook's distance does not have any distribution, so we cannot do a hypothesis test. We can't say like this DI under the null hypothesis that the ith data point is not influential, follows some given distribution. All right, so it's just like a measure. It's just a measure. Now, interestingly, what can be shown, and you don't have to show it, but let's just look at this result, is that the Cook's distance is like a multiple of some 3 terms. So I'm just interested in the ones I'm highlighting. So this guy here, you can see it's a function of the size of the leverage. And this guy here is basically it's a standardized residual. So it's the size of the residual. So that's what I was saying about the whether a point is influential, it's some combination about how influential it is. This score here for how influential it is some function of the size of residual in combination with its size of the leverage, and it in a multiplicative way. Yeah. So as in opposed to additive way. So if you have a massive residual here and the leverage is very tiny, they're going to offset each other because it's multiplicative. So then whether D is big or not depends on the relative size of these two terms. Okay, now as a guide for how big is big that warrants any attention, well, there's a lot of rules of thumb here, so don't take that's too serious, because at the end of the day, if you think you have something that needs to be looked at, you will look at it. You'll actually fit the model with it and without the point and just see what the change is, right? But as a rule of thumb, basically a value which is big, stands out from the others, may warrant attention. And here are some other rules, but I don't know where they come from. But anyway, there's no like scientific proof of why these should work. It's just big is all. So here is an exact illustration of how we could use Cook's distance. And for this, I'm going to use the credit data. Okay, I'm going to request balance on agent income. And then set up the graphics window. And first of all, yeah, so I'm going to use the built-in graphics again. So plot function. The plot function for the LM function actually contains 6 plots. So if you want to look up the documentation here, you look up, because there's different types of plot functions in R. What you want to look up is what we call the documentation. It's plot.lm, plot.lm. Okay, so that tells you it's a plot function, but it's for the LM function, which should be different for just plot on its own. Right, so the plot function, anyhow, the plot function here, I want the which here tells me which of the 6 plots I wish to display. Well, it turns out the fourth, if you look at the documentation, the fourth one returns the Cook's distance. You've got the Cook's distance here, and you've got observation numbers arranged. So here's the index number. And what you're looking for is anything, as I said, a guide, follow the guide to see anything that stands out. Well, it's numbered here, the cases, these 3 cases. Now, the way to use Cook's distance, because of the way it's constructed, you're moving one item at a time, case at a time, is you just look for the one which is like stands out way from the others. So you might think this one is far from the others, right? According to some other guidelines, there is no influential plots here. But if you think like this one warrants attention, what do? You remove it and then refit the model and just look, compare your coefficient estimates. Have they changed so much as to be of a concern? So here I'm going to fit now a model without this case 3, 2, 4. And how do I do that? Well, this is now, guys, where what you learned about subsetting data comes into play. Now, what is convenient to do when you're using LM and you want to just take out some observations is do it this way. So fit the regression as usual, but our data now I'm going to do a subset of the data. I'm going to use indexing. So I say credit data, square brackets, now it's a table, so rows and columns. So remove that row, comma, and then just leave it blank, because that means I want to retain all columns here. So I mean across all columns. So this is going to remove row 3, 2, 4 across all columns there. So you remove an entire row. And if I plot that now, then you see these numbers change slightly. So you had 122, it's still there. 2726 is still there, but now you've got 86 as well, right? So you're going to always get something like that. But the question is, okay, I remove that point. Has anything changed as to make me kind of want to look into it further? Well, if I look at these things, age, has it changed much in percentage-wise? Well, it's still the same sign. And how about these two? Well, it's still the same sign. So I might just let it go here, right? So there's nothing to say like one is right, the other is wrong. it's a kind of a subjective thing here, and whether it matters or not depends on your interpretation. For example, if the income here changed sign, and I'm interested in trying to explain the phenomena between income and balance, I would be concerned, and then I would, well, as in I would then, that means that that point 324 is influential, right? So I would remove it, discard that point. Here they're kind of close, so I'm going to just say, therefore, I'm going to retain the point 324, and then there are no Cook's distance, there are no influential points judging by Cook's distance. Now to compare the models, and this is more useful, nice table here if you want to compare models. So I'm going to show you how to compare the coefficients with and without that 0.324. So for this one, you can see the table is nice because it's got the original model here, and the model after the case 324 has been removed. And now you can see in this kind of table, compare the estimates and all the other stats. So to display such a table, which you can kind of copy and paste into Word or any kind of report, is we need this package Huxtable, because it is used for creating tables of text. And then this is how we use it. We'll go that function huxreg. Now, what is the model here? Well, that's the name of my model, the regression object. So this will be column 1, and it will be called model. So here is, you give it the name, and here is the actual regression output that you fitted. So you have to fit the regressions first. And then the second column, I'm going to call it this, and equals the output. That was the second regression model I fitted. What statistics do I also want to display? Well, okay, I want all these guys. Okay, so more on that and examples is given in the link here. So this is useful, like if you're comparing several models of the same data. Second option, apart from using the Cook's distance, which is popular, is the added variable plot, which is also popular. And the key difference here with the added variable plot is it can identify clumps or groups of influential points, whereas remember the Cook's distance, it can only be used to identify them one at a time. So the added variable plot shows the partial relationship between y and each x. Partial meaning here, it's kind of the unique kind of the relationship between y and x after stripping out all the impact of all the other covariates. So go back to the example of regressing the balance on age and income. Here is the added variable plot for that. And so what you see on the vertical axis, it says balance. And then this symbol here, a vertical with others, it's saying it's stripping its balance, stripping out or partial out the effect of all other predictors apart from age. And this is age stripping out the effect of all other covariates. And this blue line here is the slope of the blue line here is the actual coefficient of your multiple linear regression model that you fitted. That's why it's called partial, because the slope here, remember the interpretation, it's the partial effect of that covariate on the y, in the case where the predictor of the covariate is continuous. So how I'm looking for this, and you've got a similar one for income. So how I'm looking for this one, and let me do it with this plot here, is that you're looking like, this is the partial relationship, given this blue line, and you're just seeing like, are there any kind of points that determine the slope of this line? In other words, has a slope of this line been dominated by, determined solely by a few points? Here's isolated some, but it doesn't mean anything here. So you're looking for like, maybe here it's not, there's nothing here, seemingly that worries me here. But say that, let me draw something here then. I mean, say that I had so let's extend this some more, and let me just say that we have this point here, and let's say then the line looked more like this. Then I would be, since this is the only data point in this neighborhood, then I would be concerned that I then say I've got a few points, enough density to pull the thing down. So then these four here would be considered as possibly influential, and then I would want to take all 4 points out and refit and check on the fit. There is some theory that we can go into in this added variable plot. So what I want to tell you is that we can show, and I'm going to show you in the next exercise actually, that if we add a new block of covariates, then the parameters here may be solved by regressing the residual of y on x on the residual of regressing w on x. So the key line in all this kind of talk here is just saying that this is the key, right? And all this is just some information to get to this. So the result is, if you add a new block of covariates, then you can get the OLS guy for this guy of your new vector of parameters for the new covariate block by regressing the residuals on y on x, the original model without adding the new block of covariates on the residuals of w and x. I mean, so what has that got to do with the added variable plot? So when you regress the residuals here, when you regress y and x, is like, then the residuals from this is like the y, which has been stripped out the effects of x. Residuals of w on x, well, that is the residuals in that case can be interpreted as the w remaining after you stripped out or partialed out the effects on the x. So then that's what you have, and that's how it's related to added variable plot. So yeah, so it shows us the true effect or the partial effect of w with the effect of x removed. That's what the parameter would be. Right, so the results we just said there, we are now going to show clearly in this example. So look at this and attempt it. Okay, let's do it. First of all, we're supposing that delta is known. Well, w is obviously it's given because it's the data. Now, so that means this block here is known. Well, and this is beta is unknown. So what we can do is rearrange this. And what we'll actually do, oops, is the regression. We'll take this to the other side because it's known. So what we do is we create a new response outcome being this difference. All right, because now the right-hand side is in the usual format. And so this here is our kind of a just new kind of dependent variable. I'll just call it y star. And we want to find beta hat, the least squares estimator. So to do that, we solve the problem, want to minimize the residual sum of squares. That is how the OLS works with respect to the beta here. And so that is the same as saying minimize or minimize argument. It's up to you. Minimize beta. Okay, this is a residual sum of squares. I'm writing in norm notation. Or you could just write this, transpose this again. It's up to you. And from this, because it's saying in the question, you can use the usual form of the least squares estimator. So it's not asking me to prove this thing. So I'm just explaining here what I'd actually be solving. Y star. Okay. And now note this because we'll be looking at this form in the next part of the question. All right, so this question requires me to prove any properties of this hat matrix if I use them. So I'll leave that to you. I can use the usual form of the least squares estimator and the multiple linear regression setting again. Okay, well, hat matrix I need to define. All right, so this purpose of this question is to find the least squares estimator now for the new, for the delta here, corresponding to the block of new covariates. Right, so for this one, we want to solve, minimize the argument of RSS, and want to look at this respect to this delta here. Where this beta hat is from part 1. Call that line A. I want to rewrite this inside here. So now let's consider this. Remember, I'm trying to solve this, minimize this RSS with respect to delta here. Because I don't want to be writing min this norm sine squared every single line. I'm just taking this bit in here. And I'm going to kind of just write it in a form such that it looks like our usual regression, regressing something on something else. That's the idea. Right, the beta hat. See, the beta hat we know. Wow. We know from part 1. And then can you see that this I can just write as hat matrix, which I said you have to define, but if you write it, substitute in, so I'm going to leave it, just substitute this guy in, and you can see there's a hat matrix right there. Times y star, which is y. let me just y star, which is y minus. Okay, W delta. So these two, I'll gather together. These two both got a W in them. Both have got a W delta. Now, does this look like something to you? It's a residual of regressing y on x. And does this bit looks like something to you? Yeah, it's a regression of w. It's a residuals from regressing w on x. Substituting b into a. So we're minimizing with respect to delta. This. But now, compare this expression, you see, to the one that we wrote right at the start, where we wrote minimize respect to beta. The usual regression. What do we do usual regression? We write it like this, yeah? And what is the result of this? The result of this implies now compare this form to this form. Now, this y here is all that. This x here is this bit here. What am I after in this case? That was beta. In this case, it's delta. And we know the answer looks like this. So all you're going to do is you're going to combine it that way to get me this. In other words, you don't have to kind of multiply all this stuff out and do your first order conditions and set to 0 and solve. So by comparing this to this, we know the answer is in this format. So let me call this, to make it quite clear to you guys, that's what I'm doing. Let's call this y tilde. Let's call this block here w tilde. So by analogy, what we have is that the delta, the OLS for delta hat is this. Okay. And then maybe we just should substitute it out. I have not used any properties of the H matrix yet, so I'm going to use them by making a substitution for this guy into here, which gives me my mouse has frozen. Now you will need to maybe add a line here, maybe extra, because you need to show the properties of H that you're using. Basically, I'm using the property that I minus H is idempotent? Well, that is something you will have solved as an exercise in the homework. So you don't have to do it here, but I'm just saying, well, in the exam here, this question, you would have to do it, but it's something that you've done already. Why? That's why. As I minus H is idempotent, not impotent, idempotent. Okay, yeah, so we have broken this. Yeah, so this is a question that shows you about the added variable plot. Let's wrap things up now. So what have we done today? The takeaways is that we've looked at a basic workflow on how you can construct a model to meet the model assumptions, and warnings were given there about how you interpret the coefficients or what can do with the model afterwards and how you report it. So what the consequence is for OLS when each of the assumptions fail? Well, we consider the case, guys, where assumptions fail individually, but note that in practice, you can have more than one assumption failing at a time. If that happens, you have to identify which one is more serious and deal with that one first. Sometimes you find that one of the assumptions creates the other violations. Okay, a hint here is usually if you have non-linearity, that you deal with that first, because that could lead problems, the other problems that you see. And what did we do? We kind of presented all this on a table, so it's great for you guys for revision. I've presented on a single slide about all the consequences, remedies, and actions to take. I mean, actions you could take when you see a problem and how you can detect for them. We looked at one of these methods on how you can have a remedy for violations of assumptions involving transformation, that's weighted least squares, which is we'll kind of revisit in the second half of this course. What will we do in week 4 class? Well, we've been going very gently using R Studio and more of the same, I guess, this week. So this week we'll be looking at hypothesis testing and doing predictions in R, and there'll be some kind of example from finance where you can use prediction intervals to identify cheap stocks as in assets. Exercise 3, another theory, is due in week 5. All right, and I'll leave you to enjoy this week's reading. Okay, guys, so that's it. And as usual, I'll see you in class. So for now, see you then.